Anyway, so tomorrow is our final. The final is going to be 6 problems. Of those 6, 1 will be on fluids, 1 will be on oscillations, 1 will be on gravity and orbits, and 1 will be on pendulums. And then the other 2 are cumulative. And one of those cumulative is a pretty simple energy equation problem. So if you understand how to write the energy, it's not too hard, and it won't be like rotating. It'll be straight up kinetic energy, gravity, and what's the other thing? Yeah, I think that's it. It won't even have springs, so it'll just be something where you need to use energy to find the answer, although you can obviously do it another way if you want. And then we'll have one on like Newton's laws that might have a little bit of torque, meaning pulleys with masses, and we'll talk about that at the end. But what I really wanted to cover today is mostly from yesterday. We kind of covered it with the lab, but oscillations and pendulums. So I don't know which one you want to start with. I guess we can start with pendulums. They're easier than the oscillations, and we just went over oscillations, so it probably won't be so boring. But the idea behind a pendulum is that you only have one equation. You have the equation of what we call a simple pendulum, and you have the equation of a physical pendulum. And it gives you the period. The period of a physical pendulum is I over mgr. And for a simple pendulum, what R is, to make this understandable, is it's rotating about this axis, right? Going back and forth. If this were a simple pendulum, then I is m, and this is L, is ml squared. That's the moment of inertia of a point mass. It's just mr squared. And L or R is the distance from the point that it's rotating at to the mass, right? And then R is something that we call the radius of gyration, and that's the distance from the axis of rotation to the mass. So that's also L. So if I put those in here, I can see that I get 2 pi L over G, because this becomes ml. ml squared over ml is just L over G. I don't want you to try to remember the simple pendulum. I want you to remember this, because that will help you forever and ever down the road. But really, there's a few additional things that you can do with a pendulum besides that, and I'm going to show you that on this solution, the different things that we can do. So I know you probably can't see this, but this is problem 5 from the 61755 practice final, where there's an astronaut on an asteroid with a radius of 300,000 meters, asteroid spherical. He's on it, he creates a pendulum from a 1.5 meter string. And once in motion, he observes that it has a frequency of 0.165 hertz. And so that's the first thing that you need to remember, is that frequency is 2 pi times frequency is your omega. You just need to know that. We haven't spent a lot of time on that, but that's the relationship between angular frequency and what we call frequency. Frequency as hertz, angular frequency is rads per second. So we're told that this is 0.165. If you plug that in, you get the omega. And so let me plug that in. 0.165 times 2 times pi is 1.04, let's say, rad per second. So that's our omega. And once we know that, we can get the period. We could actually don't even need to get omega, but we know that the period is 2 pi over omega. And note, this omega is not the omega that it's swinging back and forth. What we did yesterday when we talked about oscillation going up and down, and we said that thing has a angular velocity omega, That's what this omega is. It's the speed of the periodic wave that describes the motion and has nothing to do with the motion. I talked about this a little bit, but the omega of the pendulum is going to be going from 0 negative to 0 positive back and forth, right? Its angular velocity constantly going to be changing as it goes back and forth. This omega is actually a constant value, and it's just the speed of this wave changing changing angle. Okay, so we could also do this to get the period, which means that we can do 1 over the frequency gives us the period. And once we have the period, period is 1 over 0.165. That's 6.06 seconds. Okay, and so once we have the period, we can find things like the length from the simple pendulum, 2 pi L over G, square everything and solve for L, and you get T squared times G over 4 pi squared. So you can put the period in there, and actually we solved for G in this problem. So we were given the length as 1.5. Sorry, I forgot we were solving for G. If I solve this for G, I can see easily that this is 4 pi squared L over T squared. And that gives me G on the surface. So once I have G, remember that G is not 9.81. G is actually the acceleration due to gravity on the surface of this thing. If force is ma, that's G m over r squared. These m's are the m of the astronaut or the pendulum or whatever, cancel. So you get that A, which is G, is actually G, the mass of the asteroid over r squared. We were told the mass of the asteroid, we were told the length and the period basically from the frequency. So we could have gotten G, and then if we wanted the mass of the asteroid, that's r squared times G over big G. And that's all done here, so I'm not going to run through those. But essentially, that's about the most you can do with a pendulum. You can find the acceleration due to gravity here. You could find the length if I gave you the period and told you what gravity was. And you could use Newton's universal law of gravity to find what G is from that. It's really just plugging stuff in. It's nothing too hard. There's a few questions on here though, because a physical pendulum now. A physical pendulum means anything that we're using as a pendulum that's not a point mass. Hi Anna, you'll have the normal time 11:15 to 4, just like always. Officially, the exam goes till 2:20, but I'll give you that extra time to make sure that you get everything scanned in, and in case there's issues with internet or you're doing this at home and someone comes and bugs you for 20 minutes, I want to make sure that you have enough time to get this all done. It shouldn't take too long, but if you know what you're doing, if you don't know what you're doing, it might take quite a while. Anyway, so a physical pendulum is anything that's not a point mass. So let's start off with a thin rod. And we go back to this equation of 2 pi I over mgr. And here's the hard part with a physical pendulum, finding r. So we know that if this thing's rotating around one end, it's ml squared over 3. That's I for a rod, and you can look that up. But r only goes to the center of mass of the object, and the center of mass is at L to the half if this thing has L, right? And so when you plug these things in, what you get is that the period here is 2 pi, 2/3 L over G. Now, you could actually make this even harder by having some weird object like a thin rod that has a sphere on the end, and it somehow comes in, and you could figure out where the moment of inertia of this whole thing is. I would have to tell you where its center of mass is, or you'd have to figure that out. So that becomes an issue. It becomes a very hard problem. That's not hard mathematically, it's just hard to make sure that you have everything set up. How you would do this is if, let's say, you were told that the center of mass of this guy here was here, and then you wanted to know the center mass of the whole system, let's say, was essentially there, and you want to know what I of this thing was rotating around here, you would have to use the parallel axis theorem that says I of the center mass plus m d squared. This is obviously L, so for the sphere here, sphere about its center was what? 3/5 of the solid, 2/5, 2/5, 2/3, whatever it is. 2/5 mr squared plus ml squared is the moment of inertia of this thing, plus the moment of inertia of the rod, right? Is, so whatever this whole thing ends up being, ml squared over 3 for the rod plus mr squared over 2/5. It ends up being a huge pain in the butt to remember. And then wherever its center of mass is, let's say the whole system has a center of mass there, which just happens to be L of the rod, then the radius of gyration is L, not that R, this R. And you would get that the pendulum is, period is 2 pi I total over mgl. That's more than I want you guys doing on the final. So if you have a physical pendulum, what you're really going to have is something like a rod, or something that's semi-easy, or at least straightforward to calculate the moment of inertia. And the only thing you need to remember is that I is not mr squared or ml squared like it is for a point mass. It's something different. And r is the distance from the axis to the center of gravity, or the center of mass of the object. And it'll be something simple if I do that. But look at the lecture on the dinosaur walking. That's a good example. If you go to the homework, we had a few pendulum problems in the homework. That was homework 10. And these pendulum problems, I believe, were towards the end. Nope, they were towards the beginning. You also have these interactive exercises on pendulums that can take you through just to make sure that you understand the forces on a pendulum. And then I think we only had, this one is a, yeah, that one is a, pendulum problem that we'll do in a second. I thought there were 2 of them on here. No, because this is actually a oscillation problem. So we'll go over those in a second. But these were really the pendulum problems. Let's do this one real fast. So if we have a thin rod with a given mass and it swings through an axis passing through one end, what that tells you is that this is a physical pendulum with a period of 2 pi I over mgr. And they gave us m here, and it swings through one end. So I, for a rod swinging through one end, is ml squared over 3. And then they told us what the period was, and they told us the mass. Period here is what, 1.8? And the mass is 0.13. And then R for this thing is L to the half. It's, or L half. It's halfway down the rod is your R. Okay. If we plug this in, we already know this is 2 pi 2/3 L over G. And then they ask, what is L for the rod? Well, L for the rod, if I square this whole thing, I get T squared is equal to 4 pi squared times 2/3 L over G. I can solve this for L, as L is 3 halves GT squared over 4 pi squared, right? So you can get your L there. And then they ask us, what is the maximum kinetic energy of this rod as it swings? And so when you do that, you need to figure out what I omega squared is plus mv squared is, right? For this thing. And I may have, did they do that right? Oh yeah, I'm being dumb. Sorry guys. I always forget this. So when you do energy, right? You know that the energy when this thing is at the top and then the energy when it's at the bottom, by conservation of energy, the energy here and the energy here have to be the same. The energy here is all kinetic energy. It'll be rotation, it'll be translation. And the energy here is all potential energy of gravity because it starts from rest. And they gave us an angle theta. So what we need is, we know this is mgh. But what is h? What is this h distance? And if this whole thing is L and this is at some angle, then this little distance here is L cos theta, and h is therefore L minus L cos theta, or the potential energy is mgl times 1 minus cos theta, where theta is given to us as 6.1. So that's another thing that you can do with pendulums, is you can ask about the energy at the bottom and the energy at the top. Just remember that if for some reason it was rotating, it doesn't actually have I omega squared because it's rotating about that axis. Oh yeah, it does. Yeah, sorry, it does have I omega squared. Plus mv squared over 2. That would be the speed of the rod as it passes through. So anyway, and since these are the same v, you could change those together, but whatever. So you could ask on like a simple pendulum, just like one problem is the ballistic pendulum. And in the ballistic pendulum, which we're not going to have, I'm just going to talk about it for a second, because I don't want to do any momentum stuff. The bullet hits the block, and then they stick together, and then they reach some height, and you say the energy here is mgh, the energy here is mv final squared over 2, where m is both masses, and the energy here is mv of this guy squared over 2, and this is nothing. Just remember that how to do energy is important, but really that's about all you can do with pendulums, all we can do. When you go on in classical mechanics, you can do things like a double pendulum, a pendulum on a pendulum. We're not going to do that. And you can do things like spherical pendulums where they swing around in a circle. We're not going to do that either. I just need to make sure that you know how to find the length of an object from its period if that object's acting like a pendulum. So I'm hoping that everyone will get the pendulum stuff, find it super easy, and move on. But yeah, just know that that's what you've got there. So let's talk a little bit about oscillations. And as you saw, if you've done the lab from yesterday, really in oscillations, we know our equations. We know an x equation, we know a v equation, and we know an a equation. We already have the form. So we've been given the equation. And that equation is what we call the amplitude times cosine times omega t. I write minus phi, your book writes phi. That just means for me, I would have a minus sign where your book wouldn't, or your book would have a minus sign where I wouldn't. It's exactly the same. It's just a perspective issue. Although technically I believe that if you've ever done waves, this is a wave traveling in the positive direction, so it needs to be this way. And when it's a positive, it's traveling in the opposite direction. So just know that. I think your book is wrong is what I'm trying to say. And there is no square there. So you know these equations, right? And really, all you have to do in oscillations to start with is figure out what your amplitude is, what your omega is, and what your phi is. So that's your job. Your job is to find x max, omega, and phi. And each of these has a different way of finding it. Or each of them may be found just from looking at a picture of what you're seeing. Because when an object moves back and forth, like our IOLab went up and down and up and down and up and down, this whole thing is 2 times x max. So half the distance it travels is your x max. So if you're told, like on the earth problems or the heart problem, you're told how much the displacement changes, you know that half of that distance is your x max. Then omega is related to period by 2 pi over omega. It's also related to K and mass. So if you're told for some reason that the spring mass is whatever, the spring constant is K, you can find the period, or you could find omega, whatever. We'll talk about this in a few problems. But basically you can get omega from either the period or the spring constant in the mass. And then finally, phi. And phi is the real problem here, because when phi is 0, our x equation, if you look at this, if phi is 0, our x equation at time of 0 is maximum. So wherever our x starts off, if it starts off with at a maximum, you know that phi is 0. If it starts off at a minimum, you know that phi is going to be pi or negative pi for our book. Pi for me, because if you put a pi in here, you get negative pi. That means that this cosine is offset by 180 degrees, or pi radians. And it starts at the negative sign and then goes, or at the negative maximum goes up. If it were here or here for some reason, where it started off at 0 for whatever reason, so it starts at the equilibrium point with some velocity, then you know that this is either pi half or 3 pi halves. It really just depends on what the velocity is doing. You know that if the velocity is initially going negative, that this thing has to be starting at maximum, or starting at, if it's initially, if the velocity is initially going to start going negative, it has to be starting at maximum and cosine is, or phi is 0. If the velocity is headed to the right initially, then you know that you're offset by either pi or negative pi. That's all pretty easy. Well, maybe not easy, but the other way that you can find phi is if you're given x at some time t is, let's say, a number, let's say it's 2, and v at sometimes t is like -3. You can put v over t is equal to x over t, and that gives you negative omega x max over x max sine omega t plus phi or minus phi. I guess I should be consistent with myself. Over cos omega t minus phi. This stuff cancels, and what you get is the tangent of omega t minus phi is equal to v over omega x at t with a minus sign. And that means arcsine or arctan of this stuff with a negative gives you this, and you could find phi by, phi is this omega t minus 10. You have to do that in one of these homework problems, and we'll talk about that in a minute. But phi is always the hard thing. Once you find phi though, you have these equations, and then you can ask a few questions. But really the hard part of oscillations is just figuring out what the heck omega, phi, and x max are. So let's look at this problem. An electric shaver, if you don't know what that is, they're the little clippers that you can use to like cut your hair. And they have a blade, or a set of blades actually, that look like little teeth, and they go back and forth. So they're telling us here that the blade moves back and forth over a distance of 0.0019 millimeters, and a frequency of 118 hertz. So right away, the first thing we have to do is we have to find omega, we have to find x max, and we have to find phi. Okay, so to start off with, we know that omega is equal to 2 pi phi. So we can plug in 2 pi times 118. We know that half this distance, this whole distance is 2 times x max. So this is 0.0019 to the half. And they didn't tell us anything about the phase on here. So we're going to assume that the phase is 0, okay? I know that doesn't, we're actually not even going to think about the phase, to tell you the truth, because what they want is they want the amplitude. They're asking you for x max. So that's 0.0019 divided by 2, although notice Wiley Plus is asking you for millimeters. So it's 1.9 divided by 2. But then they're asking you for the maximum velocity and the maximum acceleration. And we know that v of t and a of t are negative omega sine omega t minus phi, or plus phi for your book, with an x max, xm cos. And so for this to be a maximum, this argument has to be pi half. So just assume that this is 2 for the maximum and take the absolute value. V max is omega xm. A max, the argument has to be 0 and take the absolute value, omega squared x max. So this is 2 pi f times what we just found. This is 2 pi f squared, what we just found. This is usually something that you're asked. We looked at that yesterday, a little bit in the lab too. But those are the A max and the V max. So your first thing that you do is find omega, find phi, and find x max, unless you are already given them. And then usually you're asked to find A max and V max, right? It's not too hard. Here we have a block of mass, whatever, attached to a spring, and we're given the period, and then we're told what x and v are, okay? So here we know that there's a spring involved. So we know that omega is k over m. And we can find omega, we don't know phi yet, but we're going to need it, and then xm. We're going to need to find these things. It actually asks us for xm as part A. It asks us for the position and the velocity when t is equal to 0. So we're going to need phi in order to do that. So what we've been given is we've been given the mass. We've been given k. We've been given x at 1.9 and v at 1.9. And that should tell you right away the fact that you're given these, you're going to need to find phi dividing v over x. I don't know what these are, 0.186 and 3.820. Okay, meters per second and meters. All right, so first question is, what is the amplitude? So how we find the amplitude is if we know we're actually going to have to work backwards. No, maybe not. Are we? Yeah, we're going to have to work kind of backwards here. So V over X at this T, when T is 1.9, is omega squared times sine over cosine, not omega squared. Why do I keep wanting to write that? Tan of omega T, I'm going to use plus because they do, but you'll see, I'll show you that it doesn't matter when we find phi real fast. So we know that omega is RK over M, and we can plug that in. And then we get, and that is not arctan, it's just tan. So we get that omega T plus phi is equal to arctan of negative V over X times omega. Let's actually plug in some numbers real fast here. Omega is what, 190 over 3.5? Take the square root. Square root of 190 divided by 3.5 is 7.368. Arctan of negative, make sure you're in radians, of negative 3.820 divided by 7.368 times, what is X? 1.86, I mean. And I get negative, so this is a little weird. I get that omega T minus phi is, plus phi, is negative 1.22634 rad. Now, I need to find phi from this, okay? And remember that when I wrote this, I wrote X max cos omega T minus phi, and they wrote in your book X max cos omega T plus phi, okay? So for them, phi is equal to negative 1.22634 minus omega times T, and this is, what was it, 7.368? 7.368 times T was 1.9. So they're gonna get that phi is 1.22634 times 7.368 times 1.9. They're going to get that this whole phi is negative 17.168. If you do what I usually, the way I write it, I get negative phi is negative 1.22634 or whatever. If I move the omega T over, I see that I get phi is 1.22634 plus omega T. The minus signs all cancel. And so I get that phi is negative 17.168. Now, if you do their equation, you get omega T minus 17.168. You do my equation, you get omega T. There's no minus on mine. Sorry. You get omega T minus 17.168. So it's kind of a perspective thing, I guess, is it doesn't really matter whether it's plus or minus. It just matters that you're consistent with your math. But anyway, so we see here that omega T plus phi was negative 1.22 is all I'm going to write. I guess I'll write 634. And that phi was negative 17.168. Okay. So what we need to find is we need to find the maximum amplitude. And we know that X at T was X max times cos this omega T plus phi. And that is equal to, at time 1.9, 0.186. To find X max then, I just need to put in 0.186 divided by cosine of this negative 1.22634. Let's make sure that that's right. 0.186 divided by cosine of negative 1.22634 gives me 0.5508, which is what they got. It's a little bit off because I rounded my tangent function, my arctan function. But so you can see that's all you have to do. I mean, I know that's quite a bit, but to get that. Once you know that, once you know phi, finding the other two answers to this are really simple because you have the equations, right? You have A and you have B, and when t is equal to 0, and when t is equal to 0, this is omega squared x max cosine of omega t plus phi. That goes away, and so what you get is omega squared x max cosine of phi, and phi is negative 17.168. Similarly, this is negative omega x max sine of phi at time 0. That's pretty straightforward. You just plug in those values and you're done. To make sure, let's double check answer C is the acceleration. What was omega? 7.368. 7.368 times 7.368 times 0.5508 times cosine of negative 1.22634. And I get negative 10. Why am I off? What did I forget? Oh, they want position. I'm sorry. The position when time is equal to 0 is x max cos of phi. So let's do that one. Sorry, guys, I wasn't paying attention. 7.634 times cosine of negative 1.22634. And why are you being a jerk? 7.634 times cosine of negative 1.22634 is 2.577. Oh, because I'm dumb again. I used omega t plus phi. 7.634 times cos minus 17.168 is negative 0.834. Why are you being that way? Oh, because I'm sorry, you guys. My brain's in a million places. X max is 0.55, and I just put in omega for it. 0.5508 times cosine of negative 17.168 gives me 0.06. And I'm still being stupid. 0.5508. Right? Times cosine of negative 17.168. What are you doing to me? Something weird's happening here. Why did they get minus 15? Did I do something stupid? 7.368 times 1.9 is 13. Oh, yeah, apparently I did this wrong. This is only this is 15.255. No, I'm annoyed. Yeah, so remember tomorrow when things aren't working that I screw up too. This is negative 15.226. So if I put 0.55 0.08 times cosine of negative 15.226. I get 0.488, as I should. That's all well and good. Anyway, the point being that assuming you can do this right, that you can find omega t plus phi from this equation, which we got from dividing v by x. There's that problem in your book that shows you how to use x over a or a over x and v over x. And we kind of did that in the lab yesterday too. The whole point of yesterday's lab was to give you experience doing this and finding omega, x max, and v. Okay, this is a really simple problem that was meant to give you practice with the energy associated with this. Now we know the energy at any time has to be mv squared over 2 plus kx squared over 2 for a spring that can move back and forth, okay? And this whole energy actually turns out is equal to k times x max squared over 2 at any time. So what this question is really asking you is what fraction of the total energy is the kinetic energy and the potential energy when xm or x is equal to a third of xm, okay? So if x is equal to a third of xm, right? One way you can do this is you can figure out that kx squared over 2 over kxm squared over 2 is equal to, the k's all cancel, right? And the 2's cancel. And x is xm to the third squared over xm squared. This is a ninth, right? So 1/9 of the energy. This is the potential energy of the spring. This is the potential or the total energy of the entire system. That's answer B. If you know that 1/9 is the kinetic or the potential energy, you know that 8/9 are the kinetic. So 1/9 is the potential, 8/9 is the kinetic. That's easy enough. The second part is that they say, well, what about when they're each half? So if mv squared over 2 is equal to 1/2 times kx max squared over 2, and kx squared over 2 is equal to 1/2 kxm squared over 2. They want to know what xm is, or they want to know what x is, right? At what displacement, yeah. So they want to know what x is. So solving this for x, I can see that 2 over k goes away. And what I get is that x is the square root of xm squared over 2, or xm over root 2. That's just making sure that you understand the kinetic and the potential energy of a spring. It's not meant to be a super hard problem, although it can turn you around a little bit. We already did this one. And this, don't worry about damping. I don't care about damping, and it won't be on the final. So the final one, and this is a little bit of a trick, which is why I wanted it on the homework for you. It's a little bit of a trick because you think of it as a pendulum, right? And you're like, oh, it's a pendulum. I'll use my pendulum equations. It's not a pendulum. Well, it's a pendulum, but it's not a problem you solve with the pendulum equation. They give you the x of t is equal to x max cos omega t plus phi or minus phi equation, except they give it to you. This variable can be whatever variable you want as long as it's some displacement. So this is this. And remember that omega here is how the angle changes. So think about like a pendulum going back and forth, the angle constantly going between positive and negative when measured from the center line. This omega has nothing to do with that. This omega, if we do it periodic function, this omega is the wave speed of that function. It has no physical significance in relation to the angle of the pendulum at any time. Well, maybe it does, but it would be a weird, complicated formula. What you're supposed to do here is note that you know these things are the same. Secondly, you know that the period is equal to 2 pi over this omega, and that this, for a simple pendulum, is L over G, and therefore omega is G over L. You can look by inspection. Omega is 6.6 rad. If omega squared is G over L, then L is equal to G over omega squared. Assuming G is 9.8 and omega from that is 6.6 squared, what do we get? 9.8 divided by 6.6 times 6.6. And my calculator's off. I get 0.22497, which is exactly what they got for the length of the pendulum in meters. What is its maximum kinetic energy? Now, this is a little bit weird, okay? Because what we really are being asked is what is the velocity when it gets to the bottom. Now, here's the odd thing in this problem, which I don't even want to talk about, but I'll show you the solution. Essentially, what you're looking at is you have to think of the pendulum as describing an arc, right? It's describing an arc along here, okay? And we're assuming that R is the same, so therefore, whatever this omega is as it goes through here is equal to R omega is equal to RS, okay? And therefore, you need to figure out what this distance is. Well, that distance is S, okay? No, I'm actually being a little... This is saying, yeah, I'm being totally dumb. Forget what I just said. I'm confusing myself. What I meant to say was that B is equal to R omega, and R omega is actually S times omega, but S here, this length, is really L times theta. So you get L theta omega, where this is theta max, okay? And that gives you V. Once you have V, you can just plug in MV squared over 2 if you want. It's a weird problem that's kind of difficult. I threw it on there for you just so that you would see it. It's one of those weird problems, but you'll never have that on an exam. What I would do is what we did before with the height, where you know that the kinetic energy is equal to the potential energy. We just did that. So, okay, now that we've done this, let's go back to the practice exams, because I want to talk about the 2 oscillation problems on these practice exams. I know that someone was a little bit confused yesterday on one of them, and I want to take you through that. And then I want to take you through something kind of simple. So what is our first job when we do an oscillation problem? And this last problem here is an oscillation problem. Our first job is always to write down omega, phi, and x max, so that we can get this equation that is x max cos omega t minus phi or plus phi, whichever way you want to write it. So we need to find omega, and we need to find phi, and we need to find x max. This particular problem is something interesting that you may not know. The Earth actually bulges. It swells and compresses, strangely enough. Those are well known to geophysicists. It does it in all sorts of directions, but we're only talking about one of them here. And So in these processes, we're told that there's this oscillation has a period of 3, 2, 3, 4 seconds. What does this tell you? This gives you omega, right? This gives you omega because omega is 2 pi over this t. So we now have omega. We can determine the period by measuring the time it takes, blah, 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 blah. And so we find that. And then we need to determine X max. And one clever way is to take the minimum and maximum gravity. So when you're trying to find X max, right, what you need to do is find where the equilibrium is and find the X, the negative X max and the positive X max. So what we're saying here is that the Earth swells, right, outward and compresses. Actually, we're going the other way. I should really look at it from this side. That it swells up and it compresses, swells up and compresses. How we're going to find this is by measuring when G is here, right? We know that that's equal to Gm over R squared. And when G is here, we know that that's equal to Gm, call this R compressed and R expanded, right? Or R1 and R2. And therefore, you're told what these G's are, these little G's. So you know that R is Gm over G square root. And so we can find the difference between this side and this side by going R expanded minus R compressed, which is equal to square root Gm over G when it's expanded minus square root of Gm over G compressed, and then take half this value. That's what I had them do here. They found that, took half that value, because it's half the distance of the full displacement. And that's how we get our X max, is you just look and figure out how far is it going from minimum to maximum and take half that value. Hopefully you can do that. And then the last thing we have left is what is our phase? And we're told, I believe, that we need to determine phase, that at a time of 1617, we determine X at that time, and we determine V at that time. And so what we just did for that other problem, you do here for the phase. And you find that it's pi fourths. Then what I ask you for is I ask you to write the equations. And what I want is I want you to basically physically write xm cos omega t minus phi, and then plug in all your numbers. So let's say this is 4 cos 2.2 t minus 1.5 or something, whatever. I want you to actually always put those numbers into your equation, okay? Because that's actually the goal. And then what time is gravity a minimum? What time is gravity a maximum? So basically what we're saying is when is R greatest, when is R least, and what time does those happen? So if we look at this thing and we know that it's, I don't know when it started. It was at pi fourths, right? So how you could do this is find when X is a max, find the time. So when X max is equal to xm cos omega t minus phi, this occurs when this is equal to 0, right? So if you know what phi is, if omega t minus phi is equal to 0, then omega t is equal to phi and t is equal to phi over omega. And it's a min, it's equal to 0, or V is a max when X max times omega with a negative sign times sine of omega t minus phi. So when this is equal to pi half. So when omega t minus phi is equal to pi half, that means that when t is equal to phi plus pi half over omega, I believe is what we did there. And we knew what phi was, so you can see that phi is plugged in with a pi force there. But basically, this is the real part, is that the velocity is the maximum when the argument of sine equals pi half. And the displacement is the maximum when the argument of cosine equals 0, or pi, technically, because you could take the absolute value. Okay, in the other one, and this is where I think someone got confused yesterday, and I admit it's a little bit confusing. Was this the one I just did? We're almost done with this review, to be honest with you. Was this the one that we just did? No. This is the one I wanted. We have the human heart. And the human heart, you know, contracts just like the Earth does, and then it expands out. When it contracts, your blood pumps. When it relaxes, it expands out. So 2 times this is actually 2 times xm, right? And you're shown on here, you're told the diameter, so you're told what this d is, and you're told what this d is. And you're told the change in diameter, so the diameter outer, diameter inner, diameter outer minus diameter inner, this distance is half of it, because this whole thing is the change. So half of that is that, right? And divided by another half is our xm. So 2xm is equal to d outer minus d inner over 2, and xm is equal to d outer minus d inner over 4. Once we have that, you can see in this problem, we're told the period, and I totally messed this up, by the way. If a human heart beats 70 times a second, or 70 times a minute, 70 beats per min, there are 60 seconds in a minute, right? So this is 70 divided by, there are 70 beats per minute. Did I not mess that up? 70 beats per minute. So in 1 minute, 1 minute divided by 70 beats, that's what I'm doing wrong, is equal to 60 seconds divided by, times 60 seconds in 1 minute. 60 over 70 is actually 0.86 seconds per beat. So the period really should have been 0.86 seconds here. If the period is 0.86 seconds, you can find omega from 2 pi over the period. And then we found x max already from the diameter. And the last thing is to find phi. You're told that essentially this thing begins at maximum. It begins when it's fully contracted to the left, and we're assuming that to the left. So it begins when it's here. It begins when it's here, and we're looking at this as this is 0, this is x max, this is negative x max, and we're told it starts here. The equation xt is equal to xm cos omega t minus phi. If at 0, this has to be 0, at time equals 0, this whole thing has to be 0, so we know that phi is 0. That makes all of this much easier. The rest of this problem is finding the maximum acceleration, which we already did today. If the heartbeat doubles, then what happens to the force? Now, that's a little bit weird, because we know that A is omega squared x max cos omega t minus phi, and the force is ma, so m times this. Let me put an m in there. Now, if the period is halved, because the heart rate doubles. So it has to do 2 of them in the same time of 1 period. This is equal to 2 pi over omega times 2. So this becomes omega is pi over 2 pi over t. That means that your omega doubles. And if your omega doubles, since it's squared in the force is 4 times greater. The force on your heart is 4 times greater if your heartbeat doubles. Okay, that's all this is trying to get at. And then it asks for when does the maximum velocity and the, what is the maximum velocity and when does it occur? You know that if it starts at x max when t is equal to 0, when t is equal to pi or half the period, quarter of a period, v is at max and x is 0, v is 0. And then negative x max, v is 0, and v max and x is 0 at t, at t to the half, at t to the 3/4. And we're told that this is when it's relaxed, this is when it's contracted, and you're told what those are up here. That essentially V is maximum when it is contracted. This is when it's relaxed, contracted. That should make sense, right? No, I'm sorry, not when it's contracted. In between it being contracted and being relaxed, B is the maximum. Sorry. But that's all. So hopefully what you see from these is periods, pendulums, you have 2 pi L over G for something simple, but T is 2 pi I mg R, and you have to find R. And you might have to use F is G M over R squared to find like the gravity to put in here. But really that's about it. It really boils down to finding the radius of gyration and maybe knowing the right moment of inertia. For oscillations, it comes down to, you have this equation and you have obviously B and X as well, B and A as well. But it comes down to finding this, and finding this. So Calvin, really this equation is this equation. Because for a simple pendulum, I is m r squared for a point mass, a simple point mass, and R is R, or R is L and R is L. So what you get is when you plug that in, you get ml squared over mgl, and you get L over G. You really should think of it though as using the physical pendulum. You're just doing it on a really simple object. Okay. But oscillations, you need to know how to find XM usually from a picture. You need to find omega usually from the period. And you usually find phi from a picture, or you find these if you're given X at a certain time and V at a certain time by dividing V over X and blah, blah, blah. We've done that a couple times already. And so like in the lab it was weird because we started with A, and the A equation is exactly the same thing as the X equation, just with negative omega squared at the front. So if you're told omega, so think about it this way, X is equal to A divided by negative omega squared. So if you're told A and you're told omega, you can find X, right? That's one little tricky thing. But the last thing I want to talk about, unless anyone has any other questions on oscillations or pendulums, the last thing I want to talk about is the cumulative problems. What I really want to do is go back to exam 2 and exam 1, because I want to talk about a little bit about something Don't think that you got to run back and study these exams. But remember in exam 1, when we did this, and I'm just going to do this. Sorry, I don't want to actually do that too much. So remember we had a couple problems here that had, this one was something spinning around, but like this, a particle falling, right? And that was projectile motion. So just don't forget projectile motion in those equations. Maybe review it. But like this, these types of problems, right? And then if you look at the two that we did in the practice finals, the only difference between these is then you have these pulleys can rotate. So don't forget how to do this stuff. I will tell you this, that of the 2 questions, one of them, all you need is energy to solve it. You can solve it another way, but really you just need energy, and it won't have a spring and it won't have rotation. The other cumulative problem will be something like this. So just remember how to do like the free body diagram. This problem is a good problem. You have a mass on an incline, know those. Know a hanging mass. If you go back to our final solutions, wherever they went, let's say this one. So this is just that same kind of problem, but imagine that, what if this mass was on like an incline, right? It won't be this complicated, I promise. I won't put composite pulleys on there. Actually, yeah, I will. If I have to put one, I will probably have, maybe I won't. I won't put composite pulleys on it, I promise. But you might have a mass on an incline with a pulley. So know how to do this torque stuff for the pulleys. Just make sure and go through it. For the other one, you don't need to worry about this yo-yo problem at all. And then for the other one, I will tell you that you don't need to worry about the energy part. Is this the same? Yeah. So this whole part with energy, don't worry about it. I'm not going to make you do a pulley with blocks and masses with energy. It'll be something with Newton's equations with pulleys that actually rotate with moments of inertia, maybe on inclines, maybe not. And then it'll be a straight up energy question that you can do one of 2 ways, but I would do it with energy, which should tell you exactly what it is if you really know this stuff. And then it's a question on fluids, a question on gravity, basically Kepler orbits and universal gravity, a question on oscillations, and a question involving pendulums of some kind. Okay. These problems are actually, this is much harder than the Newtonian cumulative problem will be. It won't have, what does this thing have? 7 pulleys and 3 masses and 5 tensions and blah, blah, blah. It won't be that difficult. It'll be easier than that, but you better make sure you know how to do masses on inclined planes and connected to pulleys. There are a few little wrinkles. There are a few questions that are a little challenging. For the most part, though, you'll be perfectly fine if you understand. For oscillations, you understand how to find omega, phi, and X max. For fluids, it's not going to be buoyancy, I'll tell you that. It'll be something with Bernoulli's equation where you need to find the pressure from the other variables. The pendulum problem I haven't written yet. It's always hard to find something interesting because they're so simple. But I don't think the pendulum problem will be too hard. And then the gravity problem might be a little hard, the Kepler orbit. although if you know what you're doing, I don't think it's hard, but if you don't, it might be a little confusing. So I honestly though think that the final, if you've done your homework, if you've been doing your homework, if you've been reading the book and you've actually taken a good honest effort at the practice exams, I don't think the final's as hard as the last test was. I think it's actually a lot easier. And I think it's less mental stress too, to be honest. Most of these problems you can look up the equations that you need and just straight up start plugging stuff in. You don't need to do too much. I mean, you guys see that, right? Like, so hopefully this review is helpful. If anyone has any questions, let me know. Otherwise, study. The last thing I want to say is, if you didn't get yesterday's lab in, just knock it out. It's not meant to take very long. And you can do it in groups if for some reason you weren't here yesterday. It's due by midnight tonight. Lab 7 and 8, I think I moved to tomorrow. And the homeworks, I think, are due tomorrow night. So here's the thing though. I really don't want to accept any work after tomorrow night. I will let you email some stuff to me if it's something that, like, you realize that you were missing homework 3 for some reason and I never got it. We can talk about that, but I don't know how much grading I want to do of old stuff that should have been in already, since you've had a long time to get that stuff in. But definitely get the labs in. Knock those labs out after your final if you need to, but really they should have been done already. We've had a week. Get those in and I'll grade those. After we take the final, I'm going to grade, hopefully Friday and Saturday, I'll have all the grading of the labs and any homework people get me and whatever done. And I'll grade the finals. Your grades will be posted Monday morning with your final and your final course grade. Now, for those of you who weren't here when we first started this or didn't read my announcement, you cannot trust Canvas. If you are missing a grade, let's say that you have a quiz that you didn't take and I never put a 0 in for that quiz for you, that missing grade is not counted in your total percentage for your quiz scores. So it might say that you have 100% on your quizzes, even though you have a 0 on one of them, because the 0 is not posted in there yet. You know what you turned in and what you haven't. So if I neglect, I think I got all the 0s in for everybody of stuff that I don't have, and so you have a 0 on that. Just know that your grade, if you have missing homeworks, your homework grade might change dramatically, and it might dramatically affect your grade. I've been trying to tell you guys this. You got to get your homeworks in because it will hurt your grade. I mean, 10%, we're going to be on the normal scale, right? 70 is a C, 80 is a B, 90 is an A. And there's no pluses or minuses. You get a 90, it's an A. In fact, probably if you get around an 89, I'm willing to bump you up to an A. And I'll probably do that for everybody regardless without anybody talking to me. So we'll talk about grades on Monday. I'll send emails and stuff. But if you need to talk to me about your grade after your final, and please, please don't wait until you see your final grade posted before you get a hold of me. I know you guys are going to be panicked. I know you guys are worried about your grades. I know you're going to be worried after you take your test that, oh my God, the final went bad and I'm failing the course, or I'm getting a C and I have to transfer to USC tomorrow and I need an A. Okay. Don't email me until after you see your grade. Okay. Don't email me because you're freaking out, please. I'm going to have a bunch of people emailing me for other things. And basically my answer to you is going to be, let's talk after your grade posts. So on Monday, when you see your grade, if you disagree with it or are freaking out about it, contact me then. But please don't contact me on Sunday telling me that the test went horrible and you're worried that you're now screwed up your GPA and won't be able to transfer. Wait to send that email or text message on Monday after you see your grades, okay? And I know that's a little harsh, but so in short, we have basically, you got 24 hours. Make sure you get some sleep. As always, it'll be from 11:15 to 4. I'll be there the whole time. We'll be doing it on Zoom. If you have questions, you can ask. Um, the goal is not to fail you. This exam is not meant to be super hard so that you, so that I get half of you getting a 30 on it. The exam's meant to give problems that show me you know how to do an equilibrium or a oscillation problem, and that you know how to handle a pendulum problem, and that you know how to handle an orbit, that you can describe orbits mathematically. So I want to make sure that you know how to do this stuff. And there's a little bit of hard stuff on there, but overall it should be super easy and shouldn't be super stressful. But it's not my grades. I know you guys are all stressed. That being said too, I hope you saw that I graded all of your labs that I had. And one person, I sent a message that I needed their data table or something, their calculations. So you know who you are. I need your calculations, otherwise your grade is going to be a little bit hurt on that one. And otherwise, I think 95% of the labs are really good, you guys, and I really appreciate it. This lab thing has been so stressful because we have had to make these labs up, and I'm trying to piece together labs that other people have written and labs I'm writing and the original labs, and still give you something that doesn't feel like busy work, that's actually fun or teaches you concepts. I think we kind of did that. I think they could have been better, but we'll be better in fall because you went through the labs that we did. And I know it was rough, and I'm hopefully by spring, things will be back to normal. But I cannot tell you enough how much I appreciate the effort all of you have put in. I put a lot of effort into the class, and it's worth it when I see that you guys are really trying to learn this stuff, and that I know that it will help you in your courses further on, that we're getting a really good set of skills for you to be successful in other courses besides this one. And that you guys don't take this as a throwaway course that you just have to kind of sleepwalk through. I see a lot of work that you guys put in, and a lot of quality work that you put in. And I'm really thankful and respectful of that. So I think you guys did a great job this summer. Hopefully the final's not too hard on you, and you don't leave it thinking that your entire life is ruined because you didn't do great on a final in physics. It doesn't work that way, you guys. So anyway, if there's any questions for me, let me know. Otherwise, we can end this, and I'll post it in probably an hour. The reason why it takes so long is last time I got busy, but it always takes a while for YouTube to process videos. I don't know why. Sometimes it takes like an hour. So if you need to look for this, look for it probably around 2. It should be up. But otherwise, thank you so much, everybody. I really, really appreciate it. And I'll talk to you tomorrow morning.